Good afternoon or good morning, depending on where you are. My name is Professor Duke Orata. We are continuing with our thermodynamics lectures, and I continue encouraging you to follow those lectures so that you don't pick something at the top. You follow them systematically so that you are able to get the information and handle those operations in thermodynamics efficiently as you move stepwise, rather than jumping from the top and not knowing what is at the bottom here. Now, we want to look at Wankel engine. We have already discussed in our lectures the internal combustion engine. That's a four-stroke engine. We talked about the four-stroke engine. But there are other types of engines. In fact, even they are classified in terms of configuration of the piston. It could be a V engine and so forth, depending on how the pistons are configured. But I want specifically to look at the Wankel engine because it's a little bit different. It's a two-stroke engine, unlike the internal combustion engine, which we looked at, which was a four-stroke engine. And unlike the four-stroke engine, where we had mechanically controlled valves, remember, we had the inlet, exhaust valves, and so forth. These ones don't have valves. It doesn't have valves. So a Wankel engine basically is an eccentric rotary engine in terms of design. It's a two-stroke. Has no valves. Eccentric rotary design. The engine is a rotary design. Now, the best way to understand it, let's look at how does it look like. Let's just look at schematic of the Wankel engine. So, this engine, the unique bit of it is we have this triangular rotor. The rotor is actually similar, kind of similar to a Reliux triangle. So it has a triangular rotor, similar to a triangle. What's a Reliux triangle? Reliux triangle has curved edges and the width is constant. Has curved edges and the width is constant. And so when you look at the Wankel engine, we have the structure. It looks like, let's try to draw it as best as we can. Try to do it as best as we can. Do it as best as we can, doesn't look quite symmetrical. This is the casing. Let's look at the casing. And this casing, if you look carefully, it looks like it has the figure 8. It has the figure 8. And so this we talk of as being, to having kind of this casing here, is talk of it as being a pictocordial housing. But this is a pictocordial housing. Looks like a figure 8. If you look at it, it looks like figure 8. And so we have our rotor, which we said looks like a roulette triangle, which has curved edges, and of course the widths are constant. So let's just try to get it as best as we can. So we first have, let's put our plugs. Our plugs there. Plugs, that is in the case of spark ignition engine. Remember, we have compression ignition engine. So we have spark plugs for ignition. And then, of course, we have the inlet, the intake. I've done it very well. Let's try to give it a good shot. We have our inlet, intake. We have our exhaust. And so we have our rotor. Let's try to give it as best shot as we can. Let's try to give it our best drawing as we can. Remember, we have said it's like a roulette triangle with curved edges. The edges are not quite straight. So this is our rotor. And inside here, we have some teeth. Of course, it is able to juxtapose tied to the gear, shaft gear. And if you look at this particular system, we can think of it as divided into chambers. You see that it's like it's divided into chambers. And so when you ignite, when the system is ignited, in this system here we have depressions and we have surfaces, so that there's no, the flame is not spread throughout the chambers. So, in other words, the flame does not throttle into all these other chambers. So we have depressions and surfaces to avoid throttling to other chambers. So let's call these chambers, combustion chambers. Combustion chambers. And so what we are saying is that there's no throttling on ignition of flame through the chambers. And this we have done in terms of we have surfaces and we have depressions, which helps scuttle that kind of physical activity happening. And so also we have some circular disc which acts in recess to this particular piston in an indented portion. In other words, it's not a hole, but it's just a depression and an indentation, so that normally does about 3 times the speed of this rotor. And we are not going to be able to show it in terms of drawing, but there's a circular disc there. And so remember that these are chambers. And so if they're chambers, they're combustion chambers, then of course they will affect the compression ratio. They're very important in computation of compression ratios in this particular system. So the chambers, note that the rotor divide the system into chambers. I put a 1, 2, 3. And so this becomes very important in computation of compression in this particular system, those particular volumes, because of this triangular rotor will be very important in computation of compression ratio in this particular system. And so one of the things about this Wankel engine, we have already said one is a two-stroke engine. It's a two-stroke engine. So if you look at the number of machine cycles per unit time, for the four-stroke engine, this will be N, but for the four-stroke engine, will be N over 2, because this has just, you have two strokes in this particular system. Then we said it has no valves. In other words, there are no mechanical control valves like in the case of the four-stroke unit or internal combustion engine. And in terms of efficiency, these units are not very highly efficient, not very efficient. And if you look at our lectures on efficiency, we said efficiency is the output energy over the input energy. Output energy over input energy. So if you look at these values, they are not very efficient. And secondly, there is emission of a lot of exhaust fumes. Emission of a lot of exhaust fumes. So this kind of systems, you'll find them used in very, very small units, power saw and those kind of things, used in very, very small units. But it's a good variant is a rotary design, which is quite unique. And of course, the movement of this rotor leads to their classification. Leads to their classification. There are those with the orbitary or planetary motion. And of course, as they move around, the one which transmits that motion to the crankshaft, transmits that motion, and it can be planetary, it can be orbitary, so sometimes it can be described as circuitous and so forth. And therefore, so you find that, for example, one which is circuitous, normally referred to as KKM in terms of the notation. So these are very important. Engines, two-stroke, simple, but performs. Especially the KKM one performs as opposed to the other version. This has been operationalized, so it actually performs. So that's a unique engine, and it's quite different from the four-stroke internal combustion engine. So let's stop at that particular point.